Today we're going to look at the properties of limits. This allows us to algebraically find the limits. In the last section we talked about graphically finding limits. So for the first property we have the limit of a constant. So if we look at the limit of a constant, so that would be f of x equals b in this case, so y equals b. That means we have a horizontal line at y equals b. If we're finding the limit, we're calling the limit in this case c. So no matter what that value of c is, the limit of a constant will always be a constant because the left side and the right side of your graph is always going to be coming to that constant value because it's a horizontal line. So that's why we say the limit of a constant is a constant. So we say the limit as x approaches c in this case for this function f of x would just be equal to b. The next one we're going to look at is the limit of x, so the identity function. So if I graph that line, y equals x. So for this one, if we're looking at the limit as x approaches c, well, if I plug c in for x, notice I would get c out for y. So from the left and the right side, you're going to be approaching that same value, which is c. So the limit of a constant is going to be that constant. So the limit as x approaches c for f of x would just be equal to c. So if we want to use those properties and find the limits, so for the first one, notice that we have the limit as x approaches 3, 4, 5. So that means we have a horizontal line at 5. If we look at the left and the right side, we know that it's going to be approaching 5. For this one, this is our y equals x line, so the limit as x approaches 3 for x is just equal to, if we plug 3 in, we get 3. The next one would be negative 8, and the last one would be 1/2. So those are just some properties of limits. So now we're going to use some properties to help us algebraically find the limit. If the number that you are finding the limit for, such in this case negative 4, is in the domain of the function, then it is easy to find the limit because all you need to do is take that number and plug it in for x and solve, because that means that the limit from the left and the right is actually equal to the value when you plug it in. So for this first one, if I plug in negative 4, we know the domain's all real numbers because this is a polynomial function. There's no variables in my denominator and no variables underneath even roots. So if I plug in negative 4 squared minus 2 times negative 4 plus 3 and simplify, this ends up giving me 27. So that means the limit of this function is equal to 27. So again, when the limit is in the domain, it makes finding it very easy by plugging that value in for x. So looking at b, the domain of this is all real numbers, so that means that 4 is in the domain. So if I plug 4 in, that means we're just finding the limit of 6 minus 4, which is just 2. So the limit of the function is equal to 2. Looking at c, same thing. This is a polynomial function. It's just not in simplified form because in order to simplify this, you'd have to multiply it out 4 times. But it's not necessary because all we need to do is find the limit of the function. So if I plug 1 into this value for x, we get 3 minus 5, which is negative 2 to the power 4, which is 16. Looking at D, so now the domain of this function is not all real numbers. This is not a polynomial. We have a square root, so we have to be careful of imaginary solutions. So if you quickly just eyeball this and plug in 0, you can notice that it's not going to make underneath my radical 0, or not 0, but negative. So that means that plugging in 0 is okay. So that means 0 is in the domain, and all we have to do is plug it in and solve. So that gives us 5 times 0, which is just 0, plus 8, so the square root of 8, which gives us 2 root 2 when we simplify. Looking at the next one, again, you have to be careful of fractional exponents because remember, fractional exponents are really radicals. So this is the cube root of 5x cubed minus 4 minus x, plus 3 all to the 4th power. So this is a cube root, and remember that cube roots, we are allowed to have negatives underneath the radical, We only have to worry about even roots. So since this is not an even root, that means the domain of this function would be all real numbers. So that means if we plug -1 in, we should get our solution. So when I plug -1 in here, I get the cube root of 5 times -1 cubed minus -1 plus 3 all to the fourth power. -1 cubed is -1 times 5 would give us the cube root of -5, and then negative becomes +1 plus 3 all to the power 4. So -5 plus 4 is just the cube root of -1 to the fourth power, which of course would -1 to the fourth power is 1, so the cube root of 1 equals 1. So that means that this whole thing is equal to 1. And of course you could confirm any of these algebraic or graphically by plugging it into your graphing calculator and looking at the limit that way. So for the next one, if I plug 3 into my equation, this is a rational function. So remember, we have to worry about variables that could make our denominator 0. And if I plug 3 into this equation, notice I get 3 squared minus 3 minus 6 over 3 squared minus 9. So that gives us 9 minus 9 in my numerator, which is 0, over 9 minus 9, which is 0. If you end up with 0 over 0, that means that you have a common 0 or common factor between the numerator and denominator that you can cancel out, which we learned when we talked about graphing rational functions. So that means there is some algebra that I can do in order to cancel out that common factor and see if it's a hole in my graph, because if it's a hole, that means I can actually find the limit. So for this, we just need to use our algebraic skills. So the limit as x approaches 3, I want to factor. So this factors into x minus 3 times x plus 2, factors in -6, so that's -1. The denominator is the difference of two squares, so x minus 3 times x plus 3. Notice that that cancels out, so that is a hole in my graph. So there is a hole at x equals 3. That means that if we simplify this, we can figure out where that hole is by now plugging the value in for x, just like we did with our rational functions, because it no longer makes our denominator equal to 0. So when I plug that 3 in, I get 3 plus 2 over 3 plus 3, which gives me 5, 6. So the limit of this whole entire function is 5, 6. Again, very similar to when we graphed our rational function. And of course, you could put this into your graphing calculator and confirm this graphically. So looking at the next one, if I plug 2 into this equation, this is a rational function, so if it gives me 0 in the denominator, then we have to look out for other techniques. So if I plug in 2, I get 2 cubed minus 2 times 2 squared plus 4 times 2 minus 8 over 2 to the fourth minus 2 times 2 cubed minus 2 minus, or plus 2 minus 2. So when I plug this in, 2 cubed, that's 8, minus 2 squared is 4 times 2 is 8, plus 4 times 2 is 8, minus 8. So the numerator gives us 0 over 2 to the fourth is 16. Oops, that's 16. And then 2 to the third is 8 times 2, so minus 16, and then plus 2 minus 2, that's also 0. So again, notice we get 0 over 0. That means that there is some algebra that we can do in order to figure out how to get rid of that so it's no longer a hole in our graph. So if we go ahead and look at this, this is 4 terms over 4 terms. Remember, we can do factor by grouping. So we group the first 2 terms and the last 2 terms. In the numerator, I can factor out x squared. That becomes x squared times x minus 2. And in the second set, I can factor out that 4, so that becomes x minus 2. And then that becomes x squared plus 4 times x minus 2. And in my denominator, same thing. I'm going to group the first 2 terms and the last 2 terms and do factor by grouping, so I can factor out x cubed there. That becomes x minus 2 plus, and here I can't factor anything out, so I'm going to write a 1 for a placeholder, so that becomes x minus 2. So then again, because those terms are the same for factor by grouping, I can factor that into x cubed plus 1 times x minus 2. And now you can see that you have that common factor between the numerator and denominator that factors out that common 0. So that becomes x squared plus 4 over x cubed plus 1. So now I'm going to look at the limit as x approaches 2 for x squared plus 4 over x cubed plus 1 because we took care of that hole in our graph. And now when I plug in 2, it no longer makes my denominator equal to 0. So then I just need to simplify. So this gives us 2 squared plus 4 over 2 cubed plus 1. So that would be 4 plus 4, so 8 over 2 cubed is 8 plus 1, it's 9. So 8/9 would be our solution. And of course, you could again plug this into your graphing calculator and look at the left and the right side to make sure that this is the correct answer. So looking at the next one, same thing. If I take 0 and plug it into this equation, it's not in the domain right away, I can see because it makes my denominator 0. But if we plug that value in, notice we would get the square root of 2 minus 0 minus the square root of 2 over 0, which gives us root 2 minus root 2 over 0, which is 0 over 0. So again, 0 over 0 means that there is some kind of algebra that I can do in order to simplify this so that I can find the limit algebraically. So for this, if that happens and you notice, well, how do I get rid of that x, and you see radicals in the equation, that should tell you right away that you want to multiply by the conjugate. In this case, we're multiplying by the conjugate of the numerator. Remember, the conjugate means you're going to change the sign of the second term, so that second terms are separated by addition and subtraction sign. So the second term is the negative root 2, so that's going to become plus root 2. So this would become the square root of 2 minus x plus the square root of 2. And if we multiply the numerator and denominator by that, it does not change our equation because it's like multiplying by 1. All right, so if I go ahead and FOIL the numerator, so this term times this term, that would give me root, if you have the same thing, you have 2 minus x squared, which is just equal to 2 minus x because you're multiplying the same thing underneath the radical, so that gets rid of that radical there. So that would just be 2 minus x, and then we have, when you're multiplying radicals, remember you multiply what's underneath, so then we have plus the square root of 2 times 2 minus x, and you can simplify that, but we're going to wait for right now. Then the inside terms would be then minus the square root of 2 times 2 minus x, and then negative root 2 times positive root 2. So remember, if you have negative root 2 times root 2, that would give us negative the square root of 4, which is negative 2, so minus 2. That's all in my numerator, so we can simplify this. But I'll do that in just a minute. In my denominator, I'm going to leave it as x times the square root of 2 minus x plus the square root of 2, and you'll see why I'm going to leave it like that in just a minute without distributing the x, because the x is the issue, so we're hoping that that's going to cancel out with something for my numerator. So notice that here I can cancel out these two terms are like terms. I also have 2 and negative 2 that are like terms and cancel out. So left in my numerator would be the negative x divided by x times root 2 minus x plus the square root of 2. And again, that's why I didn't distribute the denominator, because I knew that the x was the issue and that it should cancel out probably with something in my numerator, which now we can see those x over x is really equal to 1. So we just have negative 1 in our numerator over the square root of 2 minus x plus the square root of 2. So now if I look at this, if I find the limit as x approaches 0, when I plug 0 into my equation, it should no longer make my denominator 0. So negative 1 divided by root 2 minus 0 plus the square root of 2. So it does not make my denominator 0 anymore, so we can go ahead and simplify. So negative 1 over the square root of 2 plus the square root of 2. These are like terms, so root 2 and root 2. Remember, like terms, you your numbers in front, the coefficients are both 1, so that becomes 2 root 2. We learned that in Math 2. And of course, we're not finished because we don't like to have radicals in our denominator, so we want to rationalize this by multiplying by the square root of 2 over the square root of 2. And when we do that, we get negative root 2 divided by, and in my denominator, we have 2 times the square root of 4, so the square root of 4 is 2, so 2 times 2 is 4. So this would be my solution. So let's say we want to graphically check this. I can go to my graphing calculator and plug that into my y equals. Notice I use parentheses around what's all in my numerator divided by x. Zoom 6 would be a standard window. So here's my graph. And we're looking at 0, so I'm going to actually zoom in on 0. See what's going on at the x value. So you can see it's somewhere in there. If I hit second trace value and actually plug 0 in, I know it's not going to give me y value because remember, in the original equation it makes your denominator 0, so that's why we can't have it as a value. So if we check graphically, we can check to the right and left of 0, so 0.00001 would be to the right of 0, and negative 0.00001 would be to the left. So notice the values are coming to the same thing, so negative 0.3536. So if we then check our answer that we got, negative root 2 divided by 4, notice that is the solution that we get. So again, that's just an easy way to check your algebraic work. So let's keep going and look at the next one. So now we have a function with an absolute value. So if I plug 0 in here, I get 0 over 0. So that means there's some algebra we can do in order to solve. When you are working with absolute value functions, you have to be careful because remember, when you solve the absolute value of x equals, let's say 6, remember there's 2 solutions. You have x equals 6 or x equals negative 6. You have the positive and the negative answer. So when you are looking at the limits of 0 with an absolute value, you have to look at the left and the right side of the limit. So that means we're going to have to look at the limit as x approaches 0 from the right, means the plus sign, and the limit as x approaches 0 from the left with the minus. So that would be x squared over, and if we're looking from the right, you use the positive absolute value. So this is going to use the positive absolute value. So that'd be x. So that gives us x squared over x is just equal to x, and the limit of a constant is a constant. So in this case, if I plug in 0, I get 0. Down here, if I plug in, look at the left side of 0, if I do that, I'm going algebraically, that means I'm looking at the negative absolute value of x, so the negative x. So that would give me negative x, and when I plug in 0, the limit of constant is constant, so in this case negative 0 is the same thing as 0. So that means that the right side and the left side are both coming to the same value, therefore the limit exists and is equal to 0. And you could also graphically look at that as well. So let's go ahead and look at the next one just to show you something a little slightly different. So for this one, if I plug in negative 3, I get 0 over 0. So that means there's some algebraic work that we want to do to look at the limit. So the limit as x approaches negative 3 from the right side, and we have to look at the limit as x approaches negative 3 from the left. So anytime you have absolute value, you need to do that. So from the right means we're going to use the positive absolute value answer. So x plus 3 over x plus 3. So that's just equal to 1. So that means that the limit as x approaches negative 3 from the right side of 1 would just be equal to 1. That's the limit of a constant is equal to a constant property. Here, if we have the left side, we're going to use the negative absolute value answer. So you want to put that in parentheses because that's all on the inside. So negative of the absolute value divided by x plus 3. So that gives us the limit as x approaches negative 3 from the left would be negative 1. Notice that these are not the same. Thus, the limit does not exist because they are coming to 2 different values. So if we want to look at the graph, we can plug that in, the absolute value of x plus 3 divided by x plus 3. So if I hit graph, probably want to hit zoom 6. So here's my graph, and we're looking at the value as x approaches -3. So if I hit zoom in, oops, so zoom in on -3, you can even see just from right now that it's approaching two different values. So we can see that the left side approaches -1 and the right side values are approaching 1, thus the limit does not exist. So that is why you have to be very careful when finding the limit with absolute value that you look at both, again, the right side and the left side, or the positive absolute value answer and the negative absolute value answer. All right, so for the next one, same thing. If I look at this limit and I plug 9 in, we get the square root of 9, which is 3 minus 3, 0 in the numerator, over 9 minus 9, which is 0. So we have 0 over 0, which means there is some algebraic things we can do to get rid of that so that we can simplify and find the limit. That anytime that happens, and you notice there is that radical, you can multiply by the conjugate of what is in your numerator. So the conjugate of the numerator would be root x plus 3 over root x plus 3. So if I multiply by that, notice then I would get root x times root x, which is equal to x, and then plus 3 root x minus 3 root x, and then minus 9. Notice your middle terms cancel out to leave you with x minus 9. So in my denominator, I am not going to FOIL it out, because notice that in my numerator I got x minus 9, and that's going to cancel out with my denominator x minus 9. So we're going to leave that in factored form. So I can cancel out that term where the whole is. So that cancels out. So really I'm looking at the limit as x approaches 9 for 1 over root x plus 3. Now when I plug 9 in, it no longer makes my denominator 0, so that means this is equal to 1 over the square root of 9 plus 3, which is 1 over 3 plus 3, which is 1/6. Looking at the next one, if I plug in 4, I would get 0 over 0 for this problem if I plug 4 in for x. So that means there's something algebraic we could do in order to simplify this to get rid of the hole in our graph to solve, to find the limit. So this is a complex fraction, which we did in Math 3. So in order to get rid of our complex fraction, we want to make it one fraction divided by one fraction, because this is really over 1. So we right now have two fractions divided by one fraction. So we need to get rid of that by multiplying to get a common denominator in our numerator. So this would be 16 over 16 and x squared over x squared. If you forget how to simplify complex fractions, I suggest looking up how to do so, or you can look at my Math 3 videos. So for this, we have 16 over 16x squared minus x squared over 16x squared, and that's all being divided by the x minus 4. Now again, you don't want to cancel out that 16 over 16 or the x squared of x squared, because we did that on purpose so that we could get a common denominator to make it one fraction. So when I do that, I get 16 minus x squared over my common denominator, 16x squared, divided by x minus 4. Remember, that's really over 1. So now that I have one fraction divided by a fraction, we can keep change flip. So remember, you keep the numerator as is, change to multiplication, and flip the second fraction. So keep change flip. So now for this, that still did not eliminate our problem, which is the x minus 4. And if I look right here, I have 16 minus x squared, which is the difference of two squares. So I'm going to go ahead and factor that. So that factors into 4 minus x times 4 plus x over 16x squared times 1 over x minus 4. Then I would notice that I still don't have any terms to cancel out. So I have x minus 4 and this one right here. If I were to rewrite that, that's negative x plus 4. But notice that the signs are opposite. And I could also rewrite this one as x plus 4 so that they're in order. So if the signs are opposite like that, you have positive x here, x, negative 4, positive 4, then what you should do is factor out a negative 1. So if you factor out negative 1, that's going to make the terms the same. So take out that negative 1. That becomes x minus 4 times x plus 4 over 16x squared times 1 over x minus 4. Now I can go ahead and cancel out that common factor between the numerator and denominator. So that gives us, in my numerator, negative 1 times x plus 4 times the 1 over 16x squared. Now I've eliminated the 0, and I can go ahead and find the limits. So we're looking at the limits as x approaches 4, negative, and I can distribute that negative 1. So negative x minus 4 over 16x squared. And when I plug 4 in, it no longer makes my denominator 0 to solve. So in this case, we get negative 4 minus 4 over 16 times 4 squared, which gives us negative 8 over 256, which is, when we reduce, negative 1 over 32. So this would be the limit. So that is how we find our limits algebraically. So again, we can multiply with the conjugates. You can simplify your complex fractions. If you have the absolute value, you have to do both the left and the right side of your absolute value, the positive and the negative. And again, if it's in the domain, like these top ones, you can just plug it in. So those are the easiest ones to find the limit algebraically. But we know that if we plug the value in and we get 0 over 0, that means there's a common factor between our numerator and denominator. That's what tells us that there's some algebraic things that we can do in order to solve, to find the limit by hand. And of course, if you get stuck, you can always use your graphing calculator to plug it in and find the limit that way.